Can you see my screen?
Yep, perfect. We can see your screen and the floor is yours.
Wonderful. All right. So thank you very much for inviting me to speak at this wonderful workshop. Um, our ability to physically interact with the world relies on the continuous loop between action and perception. And of course, in physical interaction, at the core of this loop lies haptic feedback, which provides critical information that shapes both the perception and the action. Now, despite relying actually on the same signals, in many situations, perception and action can be diverged. And it is shown over the years in a range of compelling sensory illusions that reveal distinct sensory pathways for the processing of information, for perception, for action. And so this is an example for the visual information where the sizes of these circles are affected by the surrounding circles in the Ebbinghaus illusion. But when the same circles are presented to be grasps, the opening of the fingers is proportional to the actual size of the object and not affected by the illusion. Now, of course, perception also shapes action, but in a kind of higher level of goal selection and everything. Now, this dissociation is also evident when we interact with elastic objects. So here, the perception could be the perception of stiffness, and the control could be the control of grasping forces and motor execution, and each can rely on different processing of the haptic feedback. And especially the control of grip force is important because it's based on, at least its predictive component is based on an internal representation of the stiffness of the elastic object that may be different from the one that is formed for perception. Now, we're talking about haptics, and haptic is not a single stream of information. It's a rich combination of tactile signals from the mechanoreceptors in the skin and from kinesthetic signals in the muscles and the joints. And they both work together to interact with the world, to coordinate movement, and to enable perception. In my lab, we study this integration by inviting participants to the lab to interact with a robotic device that emulates an interaction with elastic object. So we apply forces on the fingers that are proportional to the penetration of the participants into the object. And in such interaction, both the kinesthetic and tactile sensors are stimulated. But in some of the objects, we also apply an artificial stretch on the fingers by a moving tactor that also moves proportionally to their penetration into the object. Now, by comparing the answers of the participants to these pairwise comparisons, we can construct psychometric curves, and the shift of the curve indicates the perceptual illusions. So here in the blue curves that are shifted to the right, the illusion is of touching a harder object when the skin is artificially stretched. And it can be represented by a single number, the point of subjective equality, and the illusion is depicted in these two plots showing that it's actually an immediate illusion. So even one probing already
camera module.
it creates a positive point of subjective equality that is actually identical to the one on the right, where the participants were free to probe as much as they wanted. Now, what about the control of grasping forces? So we can see that when skin stretch is applied in the red plot, there is a rising trend in the magnitude of the applied grip forces as the participant made repeated movement. And a careful examination of the components of grasping forces indicated here on the right-hand plot that the predictive component of the grasping forces gradually caught up with the perceptual illusion. So we initially, in the first movement, see this association between the perceptual illusions and the grasping forces, but eventually the grip forces catch up in about 4 to 5 tries. Now, in the next experiment, we wondered whether this illusion will be replicated when the direction of the stretch is reversed. So if we're talking about a positive stretch, the direction of the stretch is similar to the one that is experienced in interaction with forces in a natural stretch, and a negative stretch is a stretch in the opposite direction. And surprisingly, applying the stretch in the opposite direction did not reverse the illusion, but rather weakened it. So there were highly variable effects across participants, including some who experienced the reversed or minimal illusion. But in general, the trend was that the positive stretch caused illusion of touching harder objects, and a negative stretch caused a weaker illusion. Now, we were curious, can this perception be inferred from action signals alone? So we took the results of the stiffness discrimination experiments, the perceptual responses of the participants, and the metric that described their perception, in this case, the point of subjective equality, and took the action signals, so movement, velocity, grasping forces, and fed them to an artificial neural network, so a pair of two-layer LSTM networks that predicted the answers of the participants. Now, it's not trivial that the model will be able to predict the interaction from the action signals alone, because in the case of the artificial stretch illusion, the physical property of the object is not changed. So it's not that it's a harder object and you just pushed against it weaker, but rather the perceptual information has to shape the actions differently for the model to succeed. So this allowed us to probe whether the model could uncover the hidden influence of the artificial tactile stimulation and how the brain forms this perception. So can perception be inferred from the action signals? And the answer is pretty good, yes. So here's an example of a good prediction, the real psychometric curves of the participants and the predicted one. Here is another good prediction of the lack of illusion. And sometimes it works worse. So here there is the right effect, but wrong effect size. And sometimes even the wrong effect, where an illusion was predicted when there was no actual illusion. On average, the accuracy was well above chance. So here we see the real shift of the psychometric curve as in the answers of the participants and the predicted by the model. Participant by participant, the agreement was not so great, but on average, the effect of the illusion is explained. And this was true in the positive stretch, here in the blue and the red, and also in the negative stretch. And again, a little bit weaker, but still worked. So to summarize the behavioral results, artificial tactile stimulation can create the illusion of touching a harder spring. And the illusion is, I didn't show you, but it's weakened by the presence of visual information, and it's also robust to noise and variability. And it's weakened and not reversed when the tactile stimulation direction is reversed. Also, we showed that an artificial network model can predict the illusion based on the action signals. And now, why is that so interesting, except from telling us something about how the brain processes this physical interaction? Well, if we think about designing artificial touch interfaces, there is a core challenge in deciding how to take the rich information that comes from the haptic signals on the real haptic interaction to the limited capabilities of actuators, as good and fancy as they may be. And my take on that is that we need technology that are not only biomimetic in the sense of creating the feel of what the body feels, but also neurocognitively congruent. So it's not enough to build biomimetic systems, but we need technologies that are behaviorally and cognitively aligned with the users. This means understanding not only what the body feels, but how perception, action, and even cognition, emotion, and higher levels of interaction are affected by the artificial touch. And in this case, the models can be very useful because psychophysics and characterizing the effects of the haptic technology on the users is highly time intensive. So to get these psychometric curves, you need hundreds of hours on many participants to test even a single design parameter. Whereas if you use a model, it's a shortcut. So you can predict perception from limited interaction and guide the design quite efficiently and span many design choices. So this concludes my message. Thank my students, especially Hannah Kosovsky-Lev, who did the behavioral and modeling work, and Dr. Mor Farajan, who did the behavioral work. Thank you.
Thank you very much for the very nice talk on the haptics. So let's